Hello friends, good afternoon and welcome to my YouTube channel with my name Yukal Pachori. As you all know that I do post videos related to different topics, sometimes technical and sometimes non-technical. And welcome to my YouTube channel, to all my subscriber and to all those who are watching for the first time. I am continuing a series of the videos of the electronic devices and circuits. So let's continue our discussion. This is our fifth video and with the topic Zener diode and light emitting diode. Zener diode and the LED. We will discuss two topics today. First, we will discuss the Zener diode. The second, we will discuss the light emitting diode or the LED. Let me share my screen with you. And those of you want to know that some of you asked a question to me that how you make this video that you are visible at you are also visible and you are sharing screen. I make this video with the help of the software that is known as the Zoom, and I'm taking help of the book that is known as the Robert L. Boylsted, which is the one of the important book for the electronic devices and circuits. So let's continue our discussion on the Zener diode. Uh, Zener diode, it is a heavily doped diode. First of all, it is a heavily doped diode, and it always works in the reverse biasing, and it acts as a voltage regulator. So this is some of the discussion that you can read from this particular book. But I told you the gist of the discussion that it works in reverse bias. It is a heavily doped diode and it works as a voltage regulator. The third point is very important that it works as a voltage regulator. Now I will tell you how it works as a voltage regulator and why the name Zener. Because you just look at the symbol of the Zener diode. This is the symbol of the Zener diode and it is almost Z kind of thing. This is an inverted Z which is looking here. That's why it is called a Zener diode. Maybe named after inventor or something like that. Let me discuss with the Google why Zener diode is called Zener. Okay. So Zener diode is named after the American physicist Clarence Melvin Zener. So it is named after the inventor. So there is no point of discussion in that. It is very much clear that it is named after the inventor, Calvin Zener. Okay. Melvin Zeno. So you can look at the physicist Clarence Melvin Zeno. So this is the discussion. Now you just look at the characteristics of the Zener diode. You have seen the symbol. This is the Zener diode, and you can see the P P is connected with the minus and the N is connected with the plus. So it is the reverse bias condition. And you can see in the reverse bias condition, the diode act as a off switch, and here it is acting as a resistor, and there is a Zener current, reverse current, and the reverse voltage, and there is a kind of resistance due to the reverse biasing. Now, how does it act as a voltage regulator? You try to understand. Now look at this first quadrant. This is VD, this is ID. When the voltage is flowing in the forward current, it acts as a normal diode. There is a cut-in voltage, and beyond a cut-in voltage, the current starts flowing. So as the voltage increases, the current also increases. But look at the characteristics in the reverse bias condition in the third quadrant. So this is the current where there is no current, and at a certain voltage VZ, there is a constant voltage is supplied. There is no breakdown. Now look at, understood the point? Here there is no breakdown. Why? Because the Zener diode is heavily doped, and when it is manufactured, it is set at a certain Zener voltage, and that Zener voltage is a constant voltage that the diode will supply throughout its operation. So that Zener voltage is acting as a constant voltage regulator. Suppose the Zener diode is manufactured and its Zener voltage is set to be 6 volt, then it will constantly supply 6 volt to the appliances, to the appliances for the power. So it means it is acting as a voltage regulator. That can be understood from the characteristics. So initially I told you the 3 points. It is works in reverse bias. It is heavily doped to set the Zener voltage, and it works as a voltage regulator. Now the another point of discussion is that I have told you the characteristics. Now now you can see another characteristics. This is look at this symbol, this particular point. This is a symbol. This is the zero point 0.7 is the Zener voltage and the Zener resistance. So Vz is equals to zero point 0.7 and Rz is will be corresponding value. And the ideal Zener diode does not have any resistance. It just have a constant regulator power supply of zero point 0.7 volt. So in this particular case, this is zero point 0.7. However, it can be changed from zero point 0.7 to 7, 7 to 15, 15 to 20 or 30. Depends upon the manufacturing condition, manufacturing specification of the Zener diode. So you can see in this forward wise first quadrant, it is acting as a normal diode, whereas in this third quadrant, it is acting as a voltage regulator. It is constantly supplying the voltage, which is almost same as the Vz. So this VR is a reverse voltage. You are increasing a certain point. So this is constantly supplying the voltage of the value of the Vz. However, what happens in case of the Zener diode? If we increase the voltage beyond the Vz, the diode, the Zener diode doesn't get breakdown. However, it supplies a constant voltage which is set at Vz. That's why it is called as a voltage regulator or constant power supply. In some sense, you can say it as a constant power supply at particular voltage. So you can easily understood from this particular graph. Now continue the discussion. Like for example, electrical characteristics of the Zener diode at 25 degrees Celsius ambient temperature. 25 degrees Celsius means 273 plus 25. It is 8, 298 Kelvin. So the conditions, electrical characteristics of the Zener diode at 298 Kelvin will be Zener voltage will be 10 volt, test current 12.5, dynamic impedance 8.5 ohm, maximum knee voltage is knee current and knee resistance is 700 ohm. So these are the characteristics that you can see, and these are the typical characteristics. And on these characteristics, you can work out that particular diode. You can take a screenshot with that. You can remember these. You can note down these characteristics, and these are important. Important to understand, not exactly to remember, but you need to understand what are the operating condition or what are the electrical characteristics of the Zener diode at a certain temperature. For example, 25 degrees Celsius or the 298 Kelvin. So this is the thing. These are the temperature versus Zener current graph. This is the dynamic response, dynamic impedance versus Zener current graph. So you can understand the operation with these two graph, number one graph and number two. Number one is temperature coefficient, temperature versus current. Other is impedance versus current. So you can see the plot and get the understanding of the data that or information that I'm trying to give to you. So now you can see the Zener diode. Zener potential of a Zener diode is very sensitive to the temperature of operation. I told you in the beginning that it acts as a voltage regulator. So however, this voltage regulation is temperature dependent. Means its operation depends on the temperature. Means the regulated voltage may vary depending upon the temperature. And how does it vary? You can see the temperature Tc is delta Vz over Vz, T1 minus T naught into 100% per degree Celsius. So percentage per degree Celsius. So there is a change in percentage per degree Celsius of the temperature coefficient of the Zener resistance. The statement says that, let me highlight this particular statement in the, this is highlighted. So what is the statement? The statement is Zener potential of a Zener diode is very sensitive to temperature of operation. And you can predict this temperature coefficient with this particular formula. Predict or you can calculate, and which is given in terms of unit of percentage per degree Celsius. And these are the parameters T1, T0, Tc, Vz. Vz is a nominal Zener potential at 25 degrees Celsius. Tc is a temperature coefficient. T0 is a room temperature. T1 is a new temperature table. Suppose initially you has T0 and you move to T1. So the difference between the T1 and T0 will be considered as per this particular formula. Now, continue the discussion. You can solve this particular numerical, the example 1.5. This is for the practice. You can see it. You can see the result and you can analyze it. Now, we are coming to our a new topic that is known as the LED. Uh, Okay, so look, before coming to the new topic, let me discuss the symbols of the identification marks and the symbols of the Zener diode. This is the symbol of Zener diode. You can see this is a kind of a Z over here. In this, this is line, straight line. This is kind of a Z. This is the symbol of the Zener diode. It is almost similar to the symbol of the normal diode. However, only the Z differentiate it from the symbol of the normal diode. And this is also B, means maybe notated. This is L, anode, cathode, positive, negative. This is a kind of a block diagram. And this is another symbol of Zener diode. This is another symbol of the Zener diode. But standard is the first one. However, these are the other standard Zener terminal identification and the symbol. So you understood that why it is called Zener diode, because it is named after the scientist and it acts as a voltage regulator. Now, continue the discussion. Move on to the next topic. The next topic is the light emitting diode. Light emitting diode, in short form, it is known as the LED. LED. LED are of what is LED? Suppose you are sitting in a car or you are watching a TV, or your these days home appliances are also made up. Home appliances, homes light appliances are also made up of LED. So that's why earlier it was the tube light or the fluorescence light or the like you CFL. But nowadays, totally the electrical appliances, light for the application of the light in lightning in the home, they are almost 100% LED. Why? Because they consume less power and they give a soothing light which is does not affect our eyes. That's why the growth of LED is coming over the period of time, which is increasing over the period of time. Now let's understand what is LED. LED, first of all, it is with the name that is known as the light emitting diode. It is called as a light emitting diode. And other thing, it is made up of different types of material. For example, let me read the statement and let me highlight it before reading. So the statement is silicon and germanium diodes. The greater percent of the energy converted during recombination at the junction is dissipated in the form of heat within the structure and the emitted light is insignificant. So this is very important point. What happened in the case of the silicon and germanium? The energy is dissipated, but it is dissipated in the form of heat. However, in certain material that we will discuss in the coming part of the video, that in certain materials, the energy is dissipated in the form of the light. And what are these kind of material are known as? These are known as the direct band gap semiconductor. However, in indirect band gap semiconductor, the energy is dissipated in the form of the heat, and in band gap semiconductor, the energy direct band gap semiconductor material, the energy is dissipated in the form of light. So this is the difference. So the silicon and germanium are the example of the indirect band gap. However, the gallium arsenide and the other material that we will come that diodes constructed of gallium arsenide emit light in infrared region. So gallium arsenide also emits lights, but it is in infrared region. And infrared region is not visible with the naked eyes. We have to wear spatial spectacles to see the infrared or the invisible zone of the light. Now, let me talk about the discussion. Let me talk about the discussion that which, what are the materials which emit light in the corresponding visible range. For example, if you want to have an umber color LED, umber is a kind of a orange or yellow mix color. For that, you need to have a aluminium, indium, gallium, and phosphorus. And for that, you need to have typical forward voltage 2.1. If you set the 2.1 forward voltage and use this material, for example, aluminium, indium, gallium, phosphorus, then you will have a light energy which is emitted in the form of the light and it will show the color as amber. So similarly, you can note the blue. Blue is very costly and blue is very discovered after a lot of time. And the scientists discovered the blue, the gallium and nitride. So you need to have a voltage of 5.0. And if you see this table, this the highest forward voltage is for the blue only. Green is for the gallium phosphide. orange is for the gallium arsenide phosphide, red is for the gallium arsenide phosphide. So the orange and the red are also at the same material, but the different voltage. 2.0 is for the orange. If you have the 1.8 with the same material, you will have the red. The white is gallium nitride at a voltage of 4.1. You can see the gallium nitride is giving the blue, but the voltage level is different. So see, you need to have the material difference as well, plus the voltage, forward voltage difference as well. These two corresponding combination will generate the color of that corresponding LED or the light emitting diode. It has a phenomena that is known as the electroluminescence. I am just highlighting this particular point. This is known as electroluminescence. Electroluminescence means there is a diode, and if suppose like there is a process of this is hole, this is electron, minus is electron, plus is hole. They get recombined. When they recombine, they emit energy, and the energy is released in the form of either in the heat or in the form of the light. If there is a heat, then it is a indirect bandgap semiconductor material, or if there is a light, then it is a direct bandgap semiconductor material. And we already discussed which kind of material emit which kind of light. And you can see this is the symbol of the uh, light emitting diode. This is plus, this is minus, and this is the P type, and this is N type, and this arrow kind of thing denotes the light. So this is plus, minus, and ID. VD is the voltage across the diode, and ID is the current through the diode. So these are the things which are related to the LED, and let's understood what is the corresponding the frequency. Frequency is associated lambda is equals to mu. If suppose f is a frequency, mu is equals to c over lambda, and if you need to calculate the wavelength, then you need to have the c over c f. What is c? C is the speed of the light, and what is f? F is a frequency which is measured in hertz. So you need to have the different kind of frequency to emit different kind of light with different wavelength, which is denoted with this formula mu is equals to c over lambda, or lambda is equals to c over f. So you can see, let me start the discussion with this particular graph. You can see there is a graph between the wavelength. The wavelength is a nanometer. You can see over here. And there is a luminosity. Luminosity is the intensity of the light, which is Lm per watt kind of thing. Or we will come to know what is nanometer, what is intensity. Okay. So let me discuss what is luminosity. Mm, what is luminosity? Yeah. So luminosity is a total amount of electrical energy light such as emits per unit time. So its unit is given in watt, 1 L into watt. So 1 L is the light and W is the watt power. So this is the, and you can see luminosity, and in simple words you can say the intensity of the light is an absolute measure of radiated electromagnetic energy per unit time. So it is a, you can understood that it's a kind of energy associated with the light at that particular instant of time. So you can see it is in measured in nanometer, the wavelength is measured in nanometer, and the luminosity is Lm per watt, which is 700 is the highest. And you can see which color spreads the more is a green, which has the highest luminosity, and which color spreads the least, this is the red. And you can understood with this with the Vigueur pattern as well. The red is the least spread, whereas the green is the highest spread. And after that, yellow, then is amber, then is orange, then is blue. Least is red, and the highly spread is green. So you can understood the definition between the luminosity and the wavelength with this particular graph. It shows what is the definition of this graph. This graph is the standard response curve of human eye, showing the eye response to light energy peak at green and falls off for blue and red. So this is the response for an human eye. That human eye sees the green color more and least the red color. However, the red color is visible from the far distance. Why? Because it doesn't spread that much. but the green color will not be seen from the far distance because it spreads much. So these are the things that is showing the eye response to the light energy, peak at green and falls off for blue and the red. Now you understood with this particular graph that what is the idea behind this particular graph. So this is a calculation. If you need to calculate the energy associated with the light, then you can hc over lambda. H is the Planck constant, which is 6.626 into 10 power minus 34, 34 joules per second, and c is the speed of the light. Lambda is the wavelength. You can calculate the energy associated with the that particular light in terms of joules with the hc over lambda. You can use this particular formula for the, like for example, for silicon Eg is equals to, this is important, for silicon Eg is equals to 1.1 electron volt and wavelength is equals to 1130 nanometer. And for gallium arsenide, it is 1.3 electron volt, and the energy wavelength is 8.69 nanometer. So you can have the discussion about the wavelength and the energy associated with them in terms of electron volt and in terms of the nanometer. Now, the wavelength and the frequency of the light, specific color, are directly related to the energy band gap of the material. This is another important statement. Let me highlight this. It says that the corresponding wavelength and the corresponding frequency are associated with the energy band gap of that particular material that we are using. We discussed gallium, aluminum, gallium, nitride, phosphorus, arsenic, and these are the material that we have used in that particular table. Let me show you once again. This is the table, and these are the different types of material that we have used. So I think that's it for the LED. And if you want to have the operation, if you are operating with the LED, then you need to have the data sheet of the LED. This is the kind of LED look likes, and you can see in the different pictures and images, and you can see it practically. This is the kind of LED that it look likes. Now, if you want to operate, if you want to work with the LED, then you need to see the data sheet of that particular LED, then only you can operate. However, this is the longest tail is the positive, and this is a short tail which is act as a negative. So if you apply the voltage across it, it will glow with the corresponding color. And there is a multicolor LED as well. Suppose if you use different types of material at that same place or juncture, then you will have the multicolor LED also. You have seen in various electronic DJ systems and various electronic lighting system, the LEDs are available. So I think that's it for our today's discussion. We talked about the LED. So before binding the video, see, this is a kind of a LED. This is also another kind of LED, A, B, and C. This is first kind, this is second kind, this is kind of a bulb, this is kind of a rod, and this is C is also kind of a bulb. Now you can see what is this? This is a LCD 7-segment LED display. LCD is a liquid crystal display where this is the 7-second display used, manufactured with the help of the LED. So if you want to use it as a 7-segment display, you need to use this particular LED 7-segment display. And if you need to display 5, then you will on A, you will on F, you will on G, you will on C, you will on D, whereas E and B will be off. And if you want to display 8, then you have to display on all the A, B, C, D, E, F, G. But if you want to display 0, then you will have to switch off the G. So with this, like suppose if you want to continue with the 1 only, then you have to on B and C, rest all will be off. So how many LEDs are there? 1, 2, A, B, C, D, E, F, G. So seven LEDs are there. That's why it is called the 7-segment LED display. So this is it in our discussion. And if you want to have the summary of the first chapter that we have discussed up till now, you can read the summary. And if you want to have the thorough summary of the discussion, then you can see the previous video of mine, previous 4 videos of mine, and this is the 5th video. And I think you will have a interesting discussion if you thoroughly follow all the videos of mine. So with this, the discussion of the first chapter of the semiconductor diode from the electronic devices and circuit theory, written by Robert L. Ballstead and other author, is completed. Now we'll meet with another topic in our next video. That will be the sixth video. So I hope you enjoyed the lecture or the discussion or the insights. And if you have any comments or suggestion, they can post it, and I'll be happy to answer all your questions, and I'll be happy to address all your suggestions. Thank you. Have a nice day.